Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics and the chapters of mechanical actions, equilibrium of body and Archimedes upthrust. This exercise was a previous one in the Brevet exams in 2004 first session, second exercise. The title of this exercise is icebergs. An iceberg is a huge block of ice that floats on the surface of water. So let me write it, okay. In order to show the danger of icebergs in marine navigation, we take a piece of ice of mass 0.135 kilogram. Let's denote this mass by m, which is equal to 0.135 kilograms. And of volume V is equal to 1.5 times 10 to the power minus 4 meter cube. And a container with a sufficient amount of water of density 1000 kg per meter cube. So let's denote the density of water to be rho W given by 1000 kg per meter cube in the SI. Now take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Now part 1, we immerse the piece of ice completely in water and we release it. Let me do here a small sketch. So suppose that this is the container having water. And this is the piece of ice. Now they are telling me that we immerse the piece of ice completely in water. So this is the piece of ice completely immersed in water and we release it. Now part A. Notice that till this moment the piece of ice is not at equilibrium because they didn't mention anything. So here in the text they are telling me it's floating on the surface of water, but yet in this case we don't know. So they didn't mention anything about the flotation of the piece of ice. So what we know is that now the piece of ice is immersed inside the water and is being released. Now part A, name the two forces acting on the piece of ice in water. So because it has a mass, then it will be directly subjected to the weight. So the weight is acting on the piece of ice vertically downward. And here let me stress the following. What does this weight represent? Does it represent the real weight or the apparent weight? So whenever we are discussing forces, so this weight may be the real weight or the apparent weight. And whenever we are discussing forces, we are always concerned about the real weight and the apparent weight. So this is the real weight. And here, because we have a liquid, then it will be directly subjected to the Archimedes upthrust force. So the other force is given by the Archimedes upthrust, F upthrust. So it's acting on a piece of ice vertically upward. The point of application is the center of gravity of the immersed part. This is the immersed part, and its center of gravity will be the center of the gravity of the piece of ice. So this is F upthrust. Now part B, give the line of action and the direction of each of the two forces. So notice that this figure is not part of the answer. Now we need to state the line of action and the direction of each of these two forces corresponding from the building properties, and they must be listed in this order: the first line of action, then the direction. Starting by the weight W, the line of action, we know that always the weight acts vertically downward, so the line of action is given by vertical and the direction is given by downward. And as we know that Archimedes upthrust always opposes the effect of the weight. So it is acting vertically upward, and the line of action is given by vertical. And the direction is given by upward. Now part C, determine the value of each force, and here the value means the magnitude. So now the magnitude of the weight, knowing the mass and G, and knowing that this weight represents the real weight, then the magnitude of the weight can be determined using W is equal to M multiplied by G. The value of M is given by 0.135. The value of G is given by 10. Plugging this on the calculator, then the value of the weight is given by 1.35. Since both M and G are expressed in the SI, so the value of W will be in the SI, which is in newtons. Then the value of the weight is given by 1.35 newtons. So here let me say that the value of the weight is given by 1.35 newtons. And they are telling me to determine the value of each force, so we need to determine the magnitude of both forces. We have determined the magnitude of the weight. It's left to determine the magnitude of Archimedes upthrust. So F upthrust is equal to what? Now let's discuss the different methods that one can calculate the magnitude or the value of F upthrust. The first trivial method is via the difference between the real weight and the apparent weight. Actually, this method doesn't work here because we don't know the value of the apparent weight. Now the other method is given by the condition of equilibrium, that is given by W vector plus F upthrust is equal to 0 vector. But notice that now the piece of ice is immersed inside the liquid and is being released. So we don't know whether it's floating here or at the surface or it's sinking, so we cannot use the condition of equilibrium. So we are left with the following choice that is given by the density of the liquid, which is denoted by rho water, multiplied by the volume of the immersed part multiplied by G. In order to determine the value of F upthrust, we must know the value of the density of the liquid. So let me write here that this is represented by rho L. So we know the value of the density of the water, which is given by 1000. We know the value of G, which is given by 10 Newton per kilogram. It's left to know the volume VI in order to determine the value of F upthrust. We don't know the volume VI, but here this is important that the piece of ice is completely immersed in water, so the immersed volume is equal to V. Then let's justify, since S is completely immersed in the liquid, and here the liquid is represented by water, then VI is equal to V. Now rewriting the value of F upthrust, so rho L is replaced by rho water multiplied by the volume of the immersed part, which is denoted, which is given by V, replacing VI by V, and the value of G. Now the value of rho water is given by 1000, the value of V is given by 1.5 times 10 to the power minus 4, and the value of G is given by 10. Plugging this on the calculator, then the value of F upthrust is given by 1.5. Since everything is expressed in the SI, rho water, V and G, then the value of F upthrust will be expressed in the SI, which is in Newton. Then the value of F upthrust is given by 1.5 in Newtons. So F upthrust is equal to 1.5 in Newtons. And now we are in part D. The piece of ice starts rising in water. Why? So they gave me the result. They are telling me that the piece of ice will rise to the surface of water, but they need the justification. So here let me say the following, that the value of F upthrust is given by 1.5 in Newtons, and the value of the weight, which is the real weight, is given by 1.35 in Newtons. Knowing that the weight acts vertically downward and F upthrust is acting vertically downward on one side, and on the other side, let's compare the magnitudes between the two forces. So F upthrust in this case, which is equal to 1.5 newtons in magnitude, is greater than W. So what does this equation mean? It means that the action of F upthrust is stronger or greater than the action of the weight. For this reason, the piece of ice will rise to the surface of the water. So the justification here consists of comparing the magnitudes of F upthrust and the weight. So let's say that the value of F upthrust is given by 1.5 newtons compared, or the weight is given by 1.35 newtons, and by comparison we need to say whether greater, equal, or less than, and in this case F upthrust is greater than W. Then let's say since the magnitude of F upthrust is greater than that of W, then the piece of ice starts to rise. Now we are in number 2. The piece of ice floats in equilibrium on the surface of water. Now, at any moment we can use the condition of equilibrium. Now the piece of ice is no more inside the liquid, floating inside the liquid. However, it's floating but at the surface of the liquid. So let me erase this. So the piece of ice is floating at the surface of the liquid. Now we can ask the following question. In this case, when it's floating on the surface of the liquid, what's the two forces acting on the piece of ice? For sure we have the weight that will not change. So why the value of the weight or the weight factor didn't change? Because simply the piece of ice didn't change. So the mass didn't change because the weight depends on m multiplied by g. So it's always acting vertically downward, and because m didn't change, so weight as a factor didn't change because the magnitude didn't change. Now what happened to F upthrust? Also the force F upthrust exists in this case. So what's the point of application of F upthrust? It is the center of gravity of the immersed part. This is the immersed part, and its center of gravity, suppose it's given here. So this is the representation of F upthrust, like this. So the important thing is that the weight didn't change the real weight. Now in part A, give the condition of equilibrium of the piece of ice. So as a title, let's write at equilibrium. Then how do you apply this condition? Always on the left hand side we will write the sum of forces acting on the solid S, and they are given by the weight and F upthrust. And on the other side of this equation we will write the zero vector corresponding for the equilibrium. We don't forget vectors on all of these three quantities, and especially the zero. This is a vectorial equation. Now moving F upthrust to the right hand side, we have that W vector is equal to minus F upthrust. What does the first equation tells us? That the effect of both forces acting on the solid S cancel each other to give us the equilibrium, which is the zero vector, whereas the second equation tells us that both forces have the same line of action, opposite direction, and same magnitude. So this is the condition of equilibrium. Part B, determine the volume V1 of the immersed part of the piece of ice. So we know that the volume of the immersed part appears in the following equation only, that F upthrust is equal to the density of the liquid times Vi times G. So let me write this equation here. We are interested in determining the value of Vi. In order to determine the value of Vi, we need to know the value of G. So this is done. We have it. We need to know the density of the liquid. So this is done. And it's left to determine the value of F upthrust. Okay, here we cannot say that F upthrust is given by 1.5 newtons because previously the piece of ice was completely immersed in the liquid. Now in this case, F upthrust is floating at the surface of the liquid. So when it was completely immersed in the liquid, this is the volume of the immersed part. So F upthrust is given by rho L times Vi times G, because Vi is completely immersed in the liquid, so V is equal to the total volume of the piece of ice times G. Now when it's floating on the surface of the liquid, F upthrust is given by the density of the liquid times Vi times G. In this case, the volume of the immersed part changed from the total volume to this volume. So in this case, the magnitude of F upthrust will change as well. So in order to determine Vi, we need to determine the new value of F upthrust, and this can be done using the condition of equilibrium because we know that the value of the weight didn't change. Now the vectorial relation is given by that W is equal to minus F upthrust. So we are interested in the magnitude. So let's say in magnitude we have that W is equal to F upthrust, but the value of W didn't change, which is given by 1.35 newtons. Then F in this case is given by 1.35 newtons, F upthrust. Now after we have determined the new value of F of thrust, we are ready to determine the immersed volume. Knowing that the immersed volume and F of thrust are related via the following formula. We are interested in determining VI, constructing the triangle of this formula. Here, because we have multiplied, then F of thrust will be at the top, rho L, VI, and G at the bottom. We are interested in determining VI, which is denoted by V1, which is equal to the value of F of thrust divided by the density of the liquid multiplied by G. The density of the liquid is denoted by rho W multiplied by the value of G. So F of thrust 1.35 divided by 1000 times G, which is 10. Plugging this fraction on the calculator, then the volume of the immersed part is given by 1.35 times 10 to the power minus 4. Since everything is expressed in the SI, so the volume V1 will be expressed in the SI, which is meter cube. So V1, which represent the volume of the immersed part, is given by 1.35 times 10 to the power minus 4 meter cube. And let me write here that V1 is equal to 1.35 times 10 to the power minus 4 meter cube. Now part 3, part A. Calculate the ratio V1 divided by V. So the ratio means the fraction V1 over V. Now the value of V1 is given by 1.35 times 10 to the power minus 4 divided by or over 1.5 the value of V times 10 to the power minus 4. Plugging this fraction on the calculator, then the value of V1 divided by V is given by 0.9. So V1 divided by V is equal to 0.9. Always, all quantities in physics must include a unit. Notice that here in this ratio I didn't include any unit for the following reason, that V1 is given by meter cube and V is given by meter cube, so meter cube goes out with meter cube. So whenever we are calculating ratios in physics corresponding for the same quantity, then the ratio has no unit. Okay, so for example here, if my answer was given by V1 divided by V is equal to 0.9 meter cube, this answer is considered to be wrong because its unit is wrong. So always the ratio in physics include no unit. Now in part B, they are telling me that the ratio V1 divided by V shows an evidence of the danger of icebergs. Explain why. So in order to explain why this ratio shows an evidence of the danger of icebergs, let me do the following. So the ratios are related to proportionality, knowing that V1 divided by V is equal to 0.9. So here 0.9 is not divided by anything, which means it's divided by 1. So V1 divided by V is equal to 0.9 divided by 1. Now if we cross multiply, then V1 multiplied by 1 is equal to 0.9 multiplied by V. So V1 is equal to 0.9 V. Since we are interested in ratios and proportionality, we know that this number 0.9 can be written as a fraction, which is equal to 90 divided by 100. So V1 is equal to 90 divided by 100. Now here I could have written that 0.9 is equal to 9 divided by 10, but because we are interested in proportionality and percentages, let's write 0.9 as 90 divided by 100 and not as 9 divided by 10. So what does this relation means? That V1 then V1 represents 90% of V. So this statement is very important. Let me explain it here. So what does it mean that V1 represents 90% of V? First, let's recall that what does V1 and V refer to. V1 is the volume of the immersed part. So this is V1. So what does V represent? V represent the outer volume. So when they are telling us that V1 represents 90% of V, which means that the majority of the volume of the piece of ice is found inside the water, because V1 represents 90% of V. So let's suppose that this actually, so the piece of ice will be like this. So the majority of the volume, which correspond to the 90% of the total volume, would be inside the liquid. So this is the immersed part. And the emergent part will only correspond to the difference between the total volume and the immersed volume, which is given by 10%. So looking at the piece of ice floating on the liquid, although this volume seems to be small, but taking into consideration that 90% of this volume is inside the liquid, so this shows an evidence of the danger of icebergs, especially when considering marine navigation. So I will continue this part here. Then let's say since the majority of the volume which is given by 90% is inside the liquid, or is immersed in the liquid, then the ratio, or let's say then this shows an evidence of the danger of icebergs. And by this we have finished solving this exercise. I hope it was beneficial for you guys out there watching it, and see you soon in another one.